I'm Jhoanne.
And I'm Louisa. Our presentation will be on albinism. So this is our table of contents. We're going to start with an introduction to get into the genetic cause, go over the different types of albinism, as well as the mode of inheritance, genetic testing, protective measures, complications, and end with our references. So what is albinism? Albinism is defined as a group of rare heterogeneous genetic disorders of melanin biosynthesis, as well as defined by abnormalities in visual system development. This will result in a variable hypopigmentation phenotype. So the type and amount of melanin you have determines the color of your skin, hair, and eyes. So melanin will also play a role in the development and function of your eyes. So albinism will be associated with decreased or absent melanin in ectoderm-derived tissues, such as your hair, skin, and eyes. This will yield a characteristic decrease in skin pigmentation. So as you can see in the picture over there, the female has no skin pigmentation, while the male has a lot of skin pigmentation. According to NOAA, which is the National Organization for Albinism and Hyperpigmentation, about 1 in 18,000 to 20,000 people will have albinism. There are two forms that we will be going over. They are non-syndromic and syndromic. So the overall genetic cause of albinism is caused by mutations. It could be missense, nonsense, or frame shift, and this mutation happens specifically in the TYR or tyrosinase gene, which is located on chromosome 11q 14-R. This gene provides the instruction for making the enzyme called tyrosine hydroxylase, which is required for the formation of melanin, as well as melanosomes in your skin and melanocytes in your eyes. So with albinism, there's going to be either an elimination or deficiency in the enzyme tyrosine hydroxylase, specifically in the conversion of tyrosine to DOPA. So this is the melanin biosynthesis pathway. So this step right here where tyrosine needs to be converted to DOPA, this is going to either be missing or deficient. So that's going to cause everything else here to either be missing or deficient as well. I will now be going over the types of albinism. As I stated before, there's two types, syndromic and non-syndromic. I will be going over this non-syndromic form, which is oculocutaneous and OCA1. So oculocutaneous albinism is an autosomal recessive disorder, and Jhoanne will be going into more detail on later on. It is the most common type of albinism, and people with this subtype will have very white hair, very pale skin, and very light eyes. There are 7 different subtypes of OCA, which are caused by mutations in one of the 7 genes labeled OCA1 to OCA7. There are 2 subtypes of OCA1, so I will be focusing on those 2 for the sake of time. The severe form is OCA1A, where there is complete absence of tyrosinase activity. So there's no melanin being produced. Whereas the less severe OCA1B, there's residual tyrosinase activity, i.e. there's some melanin being produced. So she has the severe form OCA1A. In ocular albinism, or OA, it's a rarer type, and it mainly affects the pigment production in the retina and iris. So this will obviously cause vision problems. It causes a transillumination defect. So when you shine a light in the eye of a person with albinism, you're not going to see any color in the back of the eye. This type mainly affects males, and the X-linked is the most common type. This occurs because of the mutation in the G protein coupled receptor 143 gene, which provides instructions for making the GPR protein, which is involved in the pigmentation of the eyes. So this will cause strabismus, which is cross-eye, nystagmus, which is rapid eye movements, and photophobia. And these are just some examples of people who have ocular albinism. So the GPR143, as I stated before, provides instructions for making the GPR143 protein. It's involved in pigmentation of the eyes, and it's made in the retina. The GPR protein is part of the signaling pathway that feeds and controls the growth and maturation of melanosomes. So in a normal retina, the GPR143 protein is going to signal for melanosome development, while in the mutated retina, GPR143 is going to prevent the signal to melanosome development, which will then cause tyrosine to not be converted into a series of steps to melanin. I will now be passing it on to Jhoanne, who will talk about the syndromic forms.
Thank you, Louisa. So as Louisa mentioned, she covered defects in melanin production. I'll be covering syndromic albinism, which is a defect in the packaging of melanosomes. Now, for albinism, there is the normal number of melanocytes, but a decrease in the number of melanin production. So there are different types of syndromic albinism. We have Chidiac-Higashi, Hermansky-Pudlak, Rosselli, Elahalde, and cross-McCusick brain syndrome. All of these types are variable in presentation. What I mean by that is the patient up here has Chidiac-Higashi, so blondness of the hair and light colored skin. He also presents with nystagmus of the eyes. Patient down here with Hermansky-Pudlak syndrome can also display nystagmus of the eyes and the same or similar coloring of the hair and skin. Patient down here has Rosselli syndrome, so there's silvering of the hair and on his head and on his eyebrows. A patient with Chidiac can also display the same silvering of the hair. So that's what I mean by all types are variable in presentation. We're going to be focusing on Chidiac-Higashi syndrome for the sake of time. So for this Chidiac-Higashi syndrome, albinism displays with this type of immunodeficiency. Again, patients experience hypopigmentation of the skin and hair. They also display some prolonged bleeding times and easily bruisability. There's a defect in white blood cells, so that means the patient is more prone to infection. That's because of a disabling function of the natural killer cells. For neurological issues, patients experience peripheral neurological problems. So that's everything outside of our brain and our spinal cord. So their limbs, especially their hands and feet, are going to have some numbness, some weakness, and children especially, because Chidiac-Higashi is prone to display or manifest in children, they'll experience difficulties walking and standing. And all of this is a result of a defect in the LIST gene. So what is the LIST gene? LIST refers to lysosomal trafficking regulator gene. This gene is responsible for lysosomal trafficking regulating proteins. So what I mean by that is you'll have your LIST gene, which is located between, this is just a location, IQ42 and Q43. There's going to be think of a traffic signal light. So there's red, yellow, and green. Think of that traffic light just blinking all different colors. That's going to affect the signaling to lysosomes, which in turn affects the phagocytic production. So for Chidiac-Higashi, when you look through your microscope, you'll see some defects in cells. Zoomed in, you'll see multiple granules on the cells, and this is a way that doctors can diagnose Chidiac-Higashi syndrome, aside from their signs and symptoms manifested in each patient. There are multiple mutations that have been found in Chidiac-Higashi, and because it's expressed higher in the bone marrow, treatment for Chidiac-Higashi has been bone marrow transplant, if caught early on. Okay, next we'll be covering some genetic modes of inheritance. So how do patients or people come up with albinism? The first is autosomal recessive inheritance. This is a way syndromic albinisms also get inherited. So as I mentioned, Chidiac-Higashi. And in this case, parents can have the gene, they can be carriers, but that doesn't always mean their child will be affected. It varies 1 to 4 chance, 1 to 2 chance. And next I'll be passing it on to Louisa, who'll be covering the second mode of inheritance.
So in the X-linked recessive inheritance, it's seen in some types of OA. It affects boys and girls differently. So girls who get the albinism gene will become carriers, while the boys who get it will have albinism. So if a mother is a carrier of the X-linked type, each daughter has a 1 in 2 chance of becoming a carrier, while each son has a 1 in 2 chance of having albinism. When a father has the X-linked type of albinism, his daughters will become carriers and his sons will not have albinism and will not be the carriers. And it's depicted in this picture right here. For genetic testing to test for albinism, the first test is genetic sequence analysis. It's the most definitive test and it's used to determine if a fetus has albinism. So amniocentesis is performed at 16 to 18 weeks to obtain a sample for analysis. In the tyrosinase hairball incubation assay test, it's to differentiate between tyrosinase positive and tyrosinase negative. So these two, this is a hair follicle from the father, this is a hair follicle from the mother. They're both going to be incubated in tyrosine for 12 hours, and then they're going to be analyzed. So as you can see, there's no pigment here in the father's hair follicle, whereas there's pigment in the mother's follicle. So the father is going to be tyrosinase negative because there's no pigment production, and the mother is going to be tyrosinase positive because she's showing some pigment production.
Thank you, Louisa. All right, so what are some protective measures patients or people with albinism can face? First of all, there's no cure for albinism, but there is possible cures for the immunodeficiencies that I talked about, such as Shirayaki. So protective measures that they can take are protecting their eyes with sunglasses or glasses if they're having trouble reading, visiting their ophthalmologist and visiting their doctors or dermatologists for any suspicious colorings or marks on their skin. They can also treat their nystagmus, and this will be via surgery. What are some complications patients with albinism face? Well, first and foremost, bullying and prejudice, especially with children in the US and in public schools, they do face some bullying due to the color of their skin. Now, albinism itself doesn't usually affect the lifespan. However, the syndromic albinisms do. For example, Shirayaki is very common in children and their lifespan can be drastically shortened. Other activities include they're limited by the sun, so outdoor activities. And because of their decrease in vision, some children were seen to be very clumsy when they were younger. However, that does improve with age. Now, another thing is cultural beliefs and practices. In certain cultures, it is said that intercourse with a woman who has albinism can cure AIDS. We as future healthcare providers can see the problems that that causes. However, it's something to take note of, and it's something that we're going to have to be able to tackle in our fields, balancing culture and modern or westernized medicine. Okay, these are our references. Thank you. Any questions?
So my name is Arissa, and Noah and I will be presenting thalassemia today.
So we're gonna start with the outlines, so we're gonna have the intro, balance, thalassemia, inheritance pattern, pathology, signs and symptoms, complications of diagnosis, treatment, and ending with recent findings.
So thalassemia is an inherited blood disorder where your body produces an insufficient amount of hemoglobin. So this can lead to anemia and an inefficient amount of healthy red blood cells being available for the body. And there are two main types of thalassemia, alpha and beta. And when we use those terms alpha and beta, we're referring to the hemoglobin chains where there's a deficit.
So thalassemia affects men and women both equally. So 4.4 out of 10,000 live births will have thalassemia. So 5 to 30% of people from China, South Asia, Middle East, Africa, and Mediterranean groups will be affected with thalassemia. It is still prevalent today because it does have some protection against malaria in the heterozygous state. So currently there is no effective screening method in the US to determine the numbers.
Right, so now let's get into the specific types of thalassemia. The first type we have is alpha. So alpha thalassemia is caused by an alpha globin gene deletion on chromosome 16. So there's normally four alpha globin alleles. And when you have this form of thalassemia, you're missing at least one of them. And the severity of this disorder depends on the amount of deletions that you have. So if you're only missing one gene, you're a silent carrier, meaning that it's very unlikely that you're going to display symptoms of anemia. If you're missing two, then the alpha thalassemia trait is present, meaning that you will have mild to moderate symptoms of anemia. If you're missing three genes, then you have hemoglobin H disease present, meaning that you're going to have moderate to severe symptoms of anemia. And finally, if you're missing all four, this is very rare, and it results in alpha thalassemia major, which is the most severe form of alpha thalassemia. And if a baby is born with all four genes missing, it can result in hydrops fetalis and ultimately lead to premature death of the newborn.
So here I will talk about beta thalassemia. So the main difference between alpha and beta is that alpha is on chromosome 16 and beta is on chromosome 11. So for beta thalassemia, it's a genetic disorder which is deficient in the production of beta globin chain on the hemoglobin. So it's either partial or complete beta globin chain due to its deficiency. So a single nucleotide in DNA is replaced on chromosome 11. So this will cause mRNA to be read differently, either as complete or either as completely absent, or it will be reduced. So then it will cause either heterozygous mutation, which is beta thalassemia minor. So this is when one defective beta globin gene is there, and this will cause less severe anemia. but then it can also cause homozygous mutation, which is beta thalassemia major. So this is when two damaged cells, this is the most severe type of thalassemia, and people with this condition will need frequent blood transfusions.
That makes I think gross.
There are some types there.
It's
Those are-
Yeah.
seems to me frozen because I just
Rechange, wow. Sorry, yeah. Okay.
So many.
Oh my gosh. It's showing up. Yeah, okay. Still loading. Okay. Can you click it?
Same presenters.
Presenter.
So everyone can see.
Okay. Oh, gosh.
This way or so.
Tell me to do it again.
Don't ask.
No, okay.
All right, so now we know a little bit about the specific types of thalassemias. Let's get into the inheritance pattern. So thalassemia is inherited in an autosomal recessive manner. So in the slide that was just up, we're going to be talking about beta thalassemia. So in that case, both parents were carriers for this disease. And there was a 25% chance of one of their children not inheriting a copy of the mutated gene, a 50% chance of one of their children being carriers, meaning that they'll have some mild to moderate symptoms of thalassemia. And there's a 25% chance of one of their children inheriting both copies of the mutated gene, meaning that they'll have some moderate to severe symptoms of anemia.
It's just not showing on your end, but you can see it.
But you can see it here.
So like, people might see the change size. It's just.
But it's there.
When you look at the slides,